My name is Craig Motlin. I've been an engineer at Goldman Sachs for about 10 years. I've worked on a number of projects there. JS Collections has been kind of a side project of mine for a number of years. Today, here's the agenda. I'm going to talk about some of the APIs that were lost and now are found with Java 8. I'll talk a little bit about the Streams API that came along with Java 8. And streams are really just the tip of the iceberg. There's a lot of features that we have in JS Collections that we would also like to see make it into standard libraries or language. So some of the iceberg is APIs, fluency, memory efficiency, and I have a short section about method references and a short framework comparison. All right, so what is JS Collections? It is an open source Java Collections framework developed internally for since 2004. We open sourced it in January 2012. It's there on GitHub under the Apache license. And it is meant to be either a supplement to the Java Collections framework in much the same way that Guava is a supplement, or it can be a complete replacement for the Java Collections framework. So we have our own lists, sets, and maps as well, and a whole bunch of other things. Along with the library itself, we've open sourced the training materials. We call it the JS Collections Code Kata. It's set up as a series of unit tests which fail. They have blanks, which are nulls, and you fill in the blanks. So it's kind of a fun way to learn JS Collections, and that's our second repository out there in GitHub. And all of our new hires go through it. So we have over 1,500 people who have been through the training and rising. All right, so I need to take a trip down memory lane, and I've given this talk before with my manager, Don Ra, who's the creator of the framework, and he is a Smalltalk developer, a former Smalltalk developer. And who here has worked with Smalltalk before? You know how you can tell if someone's worked with Smalltalk before? It's not a trick, they'll tell you about it all the time, they love Smalltalk. So here are the iteration patterns that were in the Smalltalk Collections framework. We call it the Dr. Seuss API because it rhymes: select, collect, detect, inject into. And these have names we're familiar with, like in other languages, like filter and map or transform. But they're the same patterns that we're used to in many other languages. And when Java 1 came along and the Collections framework shortly afterwards, all of these patterns were missing. And if you came from a Smalltalk background, it was upsetting to see. All the iteration patterns are gone. And in these two books, both by Kent Beck, they're separated by a decade. A full decade later, the patterns, the best practices are really just only focused on the containers and as late as Java 7. We have map, list, and set, but all the behaviors on them are gone. So JS Collections was really built around that idea, but it anticipated lambdas, but we didn't have lambdas until Java 8. So on this slide, on the left-hand side, you can see these Smalltalk 80 patterns that have been around forever. And in the middle column, here's the code that we've been writing in Java 1 through Java 7 to achieve the same thing, but with more lines of code. And usually the intent is buried on the inside of the loop. On the right-hand side, we have JS Collections. JS Collections, I should mention, is backwards compatible to Java 5. It only requires Java 5, but here we're using it with Java 8, so we can use it with lambdas seamlessly. And syntax differences aside, the right and the left look almost identical. And one caveat here is for the last two patterns, collect and inject into, we're actually using the new method reference syntax, and I'll talk about that more later, but we love method references. One interesting thing about the Stream API is that it uses lazy evaluation. And for a lot of patterns, that's exactly what you want. If you're going to build up a complicated pipeline of computations, you want it to be lazy and only force evaluation at the end. When you don't want lazy evaluation, if all you're going to do is one filter, let's say, and then you want back a collection, it's not ideal. And in that case, eager evaluation can lead to much more terse code. So in JS Collections, we have both. As lazy is the equivalent of stream. And so here you can see side by side, they're pretty similar. They both indicate laziness through their return types. So in a stream, if you call a method like filter, which returns another stream, that indicates laziness. As long as you're getting back a stream, it hasn't forced any computation. And similarly in JS Collections, we have the type lazy iterable. The other patterns like, for example, any satisfy, any match, which return true if any of the elements satisfy the condition, they return a Boolean, so there's no way to defer that computation any longer. That forces evaluation. When you do want eager evaluation, like you want a collection back because you're going to store it in a field, then you have to jump through one more hoop. And that is to terminate the stream using the operator called collect. There's a name clash there, we have collect and it means something different. But collect takes a collector, and in the 3 examples here, for filter and for map, we're passing in the collector toList to terminate the stream. So there's 2, we call it like the bun and the meat. The bun operations are the stream and the collector, collect, and the meat of the operation is in the middle. If you want eager evaluation, it's nicer when it's right on the collection, but that was that would have been too difficult to do in Java itself. The reason, well, not difficult, but it would have interfered with people's libraries. They kept the streams API a small surface by adding one method onto collections, which is called stream, and all new methods are there. If they had put a lot of methods like, let's say they put group by, for example, right onto collection, it could interfere with anyone else who has group by, and that doesn't even just have to be collections implementations like ours, it could be ORMs, for example, since group by is a concept for ORMs as well. So it's very nice that the stream API has a low surface area, but it does mean that sometimes the code gets a little bit longer, as you see here. So we've seen a taste of Java 8 streams, and it's been out for around a year, so we've got to try it out. And my impression is that it is a great addition to core Java. It provides a lot of these iteration patterns which we have been missing for a long time. It has the interesting design decision that it's lazy by default, but in a lot of cases that's what I want. It also supports both serial and parallel iteration, and I'll get more into parallel iteration later. And it has some limited support for primitives as well. We have int stream, long stream, and double stream. And it's extensible. There's only a few methods on stream, but it's extensible through that collect pattern, where you pass in collectors. And we'll see a little bit more of that. But overall, I would say that the streams API is really just the tip of the iceberg. There's so many more features that we want, and you give me an inch and I want a mile. All of these things are features that are either in GS collections or other collections libraries that are out there. And I think it's important to think about, in future versions of Java, how can we advance this API even further? Streams is a huge step forward, but I'm thinking in terms of Java 10, what additional features should make it into the core libraries? Java 9's feature set is pretty much set, so we're talking Java 10 timelines here. So as I go through some of these features, think about which ones would you really support being in the core, which do we really know at this point are solid and really belong in the spec. So here's some of what is under the water in the iceberg. Eager iteration patterns, which I mentioned. Covariant return types on the collections protocols. What I mean here is that when you use stream, every method returns stream, not like a list stream or set stream. You're responsible for keeping track of the uniqueness and things like that, whether there's an ordering on your own. There's no new collection types. Everything is new API, new methods, new behaviors, but there were no new containers. So we don't have bags, also called multisets. There's no bimaps or multimaps. You still have to use third-party libraries for this, like ours. Set and map, the HashSet and HashMap are not memory efficient. I'll talk about some of the problems with the implementation. And there were only minor changes to them, so they still have performance problems. There are primitive streams, but no new primitive containers. So that means that you can avoid the garbage of autoboxing in the middle of a computation, but at the end, you still have to do something with that stream. Streams are like iterators. You iterate through them once, and then they're done. So if you want to store it and use these primitives that you've computed again, you have to do something else other than use a stream. And there's no immutable containers. I have some metrics here. I'm not going to go through all of them, but the most interesting one to me is the last one. It's lines of code, which is not the greatest metric in the world, but it's what we have. And the interesting thing to me was that the streams API added about 15,000 lines to the core libraries, which is an incredible accomplishment. There's a ton of new behavior in just 15,000 lines, and serial and parallel, and it's extensible. So they've accomplished a lot in very few lines and got great code reuse. By comparison, GS Collections is quite big. It's 400,000 lines of handwritten code. And within that, there's templates that generate the primitive collections. The reason is that all 8 primitive lists, for example, look very similar, so we generate them from a single template. And even bigger is maps, where we have every primitive for the key and every primitive for the value. So it multiplies out, and it generates over a million lines more. So it's quite a large library. And I don't think that all of JS collections could ever get into the core libraries. And that's why I'm very focused on finding which are the most important parts that really belong in the JDK itself. So we saw some of the iteration patterns like filter and map, and those are on strings. But the ones that I showed on this slide are pretty much it. There's not a lot of iteration patterns on a string. For these other patterns that we see in other languages and libraries that you see up here, you have to get them through collectors. And I have a few code examples of collectors. Collectors are, it's a static utility class, which we saw earlier. By static utility, I mean it's a class that you don't instantiate. You don't write new collectors. You use the factory method. It's similar in that way to the collections class, where you call sort. You don't say new collection, sort. In JS collections, we've discovered a long time ago the futility of utility when it comes to learning. The only way you know about new static utility is by reading about it or seeing a presentation about it, but it's not discoverable in your IDE. Adding a new method onto an existing interface is much more learnable because you just type dot and you do control space in your IDE and it'll show you all the methods that are available to you. There's other advantages of writing object-oriented code, which I don't even need to go into. It's kind of obvious. But static utility is a little bit harder to find. It's harder to optimize since the data doesn't live with the behavior. It can be harder to read. Whenever you come across the collect pattern, you have to read the collector before you understand what it's doing, so it doesn't read as naturally left-right. That's an aesthetic value, but when I go through the code examples, you can decide for yourself what you think is more readable. So here's the first example. Here we are comparing joining using the stream API versus make string in JS collections. So we're starting with a list of things, and we want to convert each one to a string and have a comma-separated string. Since this isn't a pattern right on string, the next place you look is on collectors, and there is a collector called joining. You create it this way. And the other thing you have to do is first convert each item to a string. To me, that feels like a mistake in the API. Obviously, if you're joining strings, you want to convert non-string objects into strings. So I would have turned this into a different collector, a collector that works on any object. But it's not too bad. You can tell what's going on. In JS collections, we have a method called makeString directly on the collection. So you can see that autocomplete would be easier here, for example. Both have similar options in that you can replace the comma. You have options of no parameters, a separator, or also a start and end string. The second example is similar, except that we immediately terminate the string. We call stream immediately terminated with collect. Here what we're doing is we're taking a list of employees and we're getting their salaries and summing. So again, sum is not a pattern that you're going to find on stream, so you would go to look on collectors, find the summing into collector, and pass in the function to get the salary. In JS collections, again, we have a pattern called, right on all of our collections, called sum of int. One other point here is the return type. I think that summing integers and returning an int is a mistake. I think it should have been a long. And that's what we have in JS collections. This sort of thing is very hard to fix after it's released, so this might be a permanent problem with the summing int collector. We'll see. Now we're looking at a bit more complicated pattern, grouping by. So here we're going to take the same collection of employees and we want to group them by their department. So we're going to get back a structure where we could query for the department and get all the employees in that department. Again, we create a stream and immediately terminate it with a collect operator, and we're building a collector similar to how we did before, where we're just passing a function. That function gets the key. For JS collections, group by is just a pattern right on the collection, so we just call it directly. Now the other interesting difference here is the return types. Like I mentioned before, Java 8 did not get multi-maps, and so grouping by is going to return a map where the values are lists. That means you have to deal with the fact that you might get null, not an empty collection. The other problem with this, in my opinion, is that I didn't say that employees is a list. It could have been a set. In that case, after grouping the employees, the groups are still going to be unique. And if they're in a random order, they're still going to be in a random, pseudo-random order. And so in that case, I would want back a map of sets of employees to indicate that they're still unique and unordered. But that's not how grouping by works. You have one type. As soon as you opt into the stream API, you lose some of the compile time information. In JS collections, since it's a return type on an interface, we can have full covariant return types. And multi-map is just the most generic. If employees were a mutable set, I would get back a mutable set multi-map. And we have all sorts of multi-maps. This pattern is it's aggregation, so it's even more complicated than group by. We start out the same way. We want to group the employees by their department. But now instead of a list of employees, I'm doing the second aggregation that I talked about before, summing. I want to sum their salaries within each department. So I'm still going to get back a map-like structure, not a multi-map though, because I've aggregated something about all the employees. Again, I have a stream that I immediately terminate, and now the grouping by, I still use a grouping by collector, but it's an override. It's not the same one before. We start with the first parameter the same, which is the get department function, and now I pass in a second collector, so I have a collector within a collector. So these collectors, as you can see, they can build up, nest, they can become quite complicated, and you can build really advanced functionality out of them. On the other hand, this one might not be the most intuitive. I think it's a little bit harder to learn how to do this. On JS collections, we're still doing aggregation, so it's still going to be a more complex pattern, but at least sum by int is a method right on the container, and you can see it's Java doc separately, and you can see that it takes two functions. Also, it returns an object long map, which is one of our primitive collections. So the longs are not autoboxed. Internally, they are primitives. And the same problem of int versus long for a sum that I mentioned before applies here, since the summing int collector is embedded here. We get back a map of wrapped integer objects when using the streams API, where I really want unwrapped longs. My final code example is the partition pattern. So here we have a collection of students, and I want to just separate out the passing and failing ones based on some threshold. So the function is the same for both, and the most interesting difference here is the return types. With streams, I get back a map where I'm going to have the two Boolean wrapper objects as keys, and the values will be, again, lists of students. It doesn't matter if I started with a set of students. After calling stream, I'm going to get back a map of lists. Again, for JS collections, we have specific covariant return types. So in this case, students was a list. After partitioning, I get back a partition list, which is our own type that has methods to get the selected and rejected items. And we will maintain order in them, for example. So if everyone passed, I wind up with a list in the same order in the selected students. Any questions on these code examples before I move on? Okay. So how do they stack up? We took a screenshot of the stack traces in IntelliJ. And all we did to get these was we put breakpoints inside the lambda that we were using on the last code example, partitioning. And there's some interesting things that you can find in the stack trace. On the left-hand side, we have the stream stack trace, and at the bottom is our test, at the top is the lambda. So just reading up from the bottom, we're immediately terminating with collect. And so a lot of the stack trace is going to be the same for everything using a collector. Because we go through collect, evaluate. I didn't start with a parallel stream, it's a serial stream. So the next one is evaluate sequential. Wrap and copy into, and for each remaining twice, and accept. All of that is the same for all of the patterns because they're all just using collect. After that, we're stepping into the accept method of the lambda, and that lambda was actually built from the collector. So that's where it starts to deviate. And you can actually see the lambda as a partitioning by lambda. It's kind of embedded in manual name. If you wanted to step through this, which I did because I really wanted to learn the streams API inside out, it's a lot more to step through when you're just looking for what's going on with your collection. But it is understandable. The JS collection stack trace has a lot more to do with partition in this case. And it's because of the fact that it's just object-oriented and it's a method on every collection. So here, after the test, we step right into partition on the abstract list that we share. And from there, it goes into our own static utility that actually performs the partition on a random access list. and then we're into lambda. So the stack trace is a little bit easier to understand, but this is sort of, it comes out of the fact that we have more code. You know, we've written partition for every type differently, where streams achieves better code sharing, but you have basically the same stack trace for everything. So I showed a bunch of examples that show off the differences in the API. You get a feel for the difference in fluency too, but I have some code examples that I want to show that really emphasize fluency. For this example, I'm going to use the Anagram tutorial, which is part of the Oracle documentation. It was written around the time of Java 5, and it hasn't been updated. It still shows Java 5 kind of patterns, so it uses generics but not streams. And I'm not going to show the old Java 5 solution. You can just find it online. But we updated it as best we could to use streams and our own API. The actual algorithm is to start with all the words in the dictionary. For each word, compute its alphagram. The alphagram is just the sorted letters, so two anagrams will have the same alphagram. So in this example, we have alerts and stellar, and when we sort their letters, it's the same key. So that becomes the key in the map. All of the anagrams become the value, one collection of values in the map. After grouping them all, we filter only the groups that have a threshold, so it's at least 8 anagrams. Then sort, descending, and print them all out, starting with the most. So here, the most anagrams was 11, and you see, we'll print them out in this format. So we rewrote the tutorial using streams, and this is the solution that we came up with. If you can do even better than this, I would like to see it. We start by getting the words, which is just a collection, and we need to opt in, so we call .stream. Then we collect using the grouping by collector we saw before. So that gives us back a simulated multi-map, but if you remember, it's a map with lists as values. Since we're only, after grouping by the key, we're not interested in the key anymore, and we only care about those collections of anagrams, so we use the values method. That's an old method, it's been on map forever, and that means it returns a collection, not a string. Right? Values gives you back a collection. So now to continue fluently calling more methods, you have to call stream a second time to get back into the stream API. And then we can do the rest of the algorithm. We filter, we call sorted, and the interesting thing here with sorted is we're using one of the new comparator methods to use a primitive comparator, so no auto boxing there. Map each to a string, and then finally print it out. In real life, I probably wouldn't do it this fluently without any intermediate variables, but I'm just trying to make a point here about fluency. For JS collections, it's slightly shorter because we don't have to call stream 2 times, but that is the main difference. But I think that the intermediate return types, if I did assign to variables, are interesting, so I'd like to walk through them here. So as I mentioned before, group by gives you back a real multi-map, and it's specific to the type that we started with. So words is a list in this example, so I get back a mutable list multi-map where the key is my alphagram type, and the values will be strings. Once you have a multi-map, we have views of the keys, values, key-value pairs. The one I want here is multi-values view, and this is the collection of collections. It's similar to map.values in this case. And here we run into a limitation of the Java type system. It's kind of a curious thing that you don't run into frequently. But generics in Java are invariant. And so that means that even though I know the inner type here, I have a list of lists basically. The inner one I cannot write that it's a list. So at runtime it is, but I just can't express that in Java's type system. So I have to say it's an iterable of iterables. And rich iterable is just our top of our hierarchy. It's the iterable plus all these iteration patterns that we're going to see. Next I can call select, which is filtering it down based on the size threshold, and filtering never changes the types, so I've still got a rich iterable of rich iterables. Here I'm sorting by size, and I really just wanted to show off the two-sorted list by method, but this does sort it in ascending order, and I want it descending. So I now need to reverse it. And I'll use the as reversed method. We follow this naming convention where anything that says as is going to return a wrapper object, and so it's a constant time or lazy operation. Anything that has 2 in the name is a linear operation that does the full evaluation. So as reversed is one of the ways you can opt into our lazy API. So here we got back a lazy iterable of rich iterables And we still know those rich intervals are lists. Next, I'm going to collect. This is our collect, not strings collect, so this means map. I'm mapping each thing to a string, and so it wound up not mattering that the inner collection were lists, because I could do that on any rich interval. And finally, I print out using each. All right, that's it for the return types here. A note on lazy evaluation. One of the cool things about strings is that you can just replace the method string with parallel string, and you've opted into parallel evaluation. That's really cool. It's not a separate thing to learn, same exact API. In fact, it's the same return type, string. You don't have a separate interface called parallel string. And that's good and bad. Like, it's a smaller API, easier to learn, but it means that you have to keep track yourself that this thing will execute in parallel, that the lambdas you pass in have to be stateless or pure functional. For JS collections, we also have a parallel lazy API. You opt into it with the as parallel method, and it doesn't default things for you like the thread pool, so you pass in your executor and your batch size. And then the important thing here is the return type. We have a specific return type. It's a parallel list iterable, so you know that even after collecting, in this case, each person's address, I still have a parallel list iterable. It still hasn't evaluated, because I know that from the return type, it's lazy. But I know that when it does evaluate, I will still have something in order. It's still list-like. In this talk, I'm really only focusing on API, and I don't have time to get into performance, but I've given a talk at QCon last summer on solely focused on parallel lazy performance, and so the video is up on InfoQ, and I go into the performance of JS collections and streams, of course, and Scala's parallel collections as well. So you can check out that video if you're interested in performance. Next, I have a note on memory efficiency. So I have this chart showing memory usage of maps, and on the x-axis I have the size of the collection, up to 1 million elements, and on the y-axis I have megabytes. The top in orange is the Java HashSet that we all use. I have two competing maps, our own, which is called Unified Map, and Troves as well. And they have different growth strategies. So HashMap and our Unified Map have this pattern where they grow with a slow slope. That's when you're adding new collisions. They both use chaining, so the collisions go into a linked list of collisions, and you have that slow slope as the collisions grow. And then there's a sharp slope when we double in size periodically. Trove uses a different strategy. It uses open addressing, so collisions go right into the array using probing. And so that you have this flat line as collisions are being added, and then a doubling in size every once in a while. So even though for each size the growth is different, if you take it to the limit, you see that Java's HashMap is using, on average, twice the memory of the other two. So why is it so inefficient in terms of memory? Well, HashMap is built on top of a table of entry objects. An entry is an interesting class. It holds the key and the value, of course. It also holds a next pointer that forms the linked list of collisions. So if there are no collisions, next is just null. It also caches the hash code, which is an interesting time memory trade-off. Obviously, it uses memory to cache it, but every once in a while you're growing a hash map, it has to double in size and rehash everything, which is pretty much the most expensive operation that you can do on a hash map. And so caching the hash code greatly reduces that cost. In terms of memory, at least, it's much better to do away with entries completely, and that's what we've done in Unified Map. We just have a double size array where we alternate key values in that array directly. When there are two collisions or more in a bucket, we replace the key with a sentinel indicating that there's collisions, and the value with an array, which is similar. It has key values alternating. This strategy uses half the memory on average. But you have to watch out for this one method, entry set. Entry set is one of those leaky abstractions. It assumes that you are basing your map on a table of entries. And if you have that table, you can just return it. But if not, you have to create them on demand. And so it turns entry set from a constant time operation to a linear operation for us. It is much better to just use our method for each key value, which takes a lambda that expects a key value and doesn't auto-box them or anything, or box them into an entry object. The picture for sets is even worse. HashSet uses 4 times the memory that it needs to, on average. The reason is that HashSet is backed by HashMap. which is a good strategy for reducing code, but it's not so efficient. Everything I said about entries still applies. And in addition, within each entry, the key is used and the value is not used. So the values are a pure waste of memory. Multiplying the doubling from both, we get 4 times memory waste on average. This picture just shows the headers and stuff on each entry object, and if you do the math, it comes out to this is a map, so it's the 2 times memory waste that I mentioned. Now, there's one more point to make about the memory waste. It's that these types, not only were they not replaced in Java 8 or improved, but if you want to build on top of them, if you want these other collections that I've mentioned, like bags, multi-maps, and bi-maps, you need to build on top of maps. So Guava has these features as well, but since they target being a supplement to Java, they didn't do anything to replace HashMap and HashSet. So their multi-maps have a very similar API, and it's a very nice API, but they have the same memory problems as the JDK, because they have to build on top of these types. One more note on memory is primitive collections. I hinted at this before, and this chart isn't totally fair because I'm comparing an array list of wrapper objects with a primitive list for either Trove or JS collections. And of course you wouldn't want to wrap integers, you would avoid that at all costs. But think about what your choices are if you're using strings. You do have these primitive strings now, but like I said before, they're like iterators. You use them once and they're done. So they're not appropriate to store in a field, let's say. If it's in a field, you're going to want to access it multiple times, or you're not going to know how long it lives. So if you do this computation and you use primitive strings in the middle, and you want to store them, you have to terminate it with collect, and you have 2 choices really for what you can do. You can terminate it in a primitive array, and that's what I think most people would choose because it's obviously memory efficient. Or you can terminate it by boxing the objects, and then you have box list or box set. I think most people would opt for the primitive array, but then you're losing all the semantic information. You don't know if there's duplicates in there. You don't know if the order is significant. You don't know if it's a list or a set. So I think that primitive strings are a huge step forward, but I'd like to see primitive collections as well. The problem is how far to take it. Like we have all 8 primitives for lists and all 64 for maps. Even more because object, it can be a key or a value as well. And that's too much code. I mentioned we do code generation. I don't think all of that can make it into the JDK itself. It's just too many methods. So we need to pare it down. The strategy of using just the 3, int, long, and double might be a nice compromise. I have a section on method references. We love method references. They're really cool. I haven't seen a feature like this in other languages that I've used, even the ones that have lambdas. When Java 8 came out, we wanted to play with the new features, and so we just used our training materials and we kind of upgraded into Java 8, and we saw what we could do with the new features. And one of the brilliant things about the implementation of lambdas is that they just compile to these functional interfaces that we've always used, like comparator and runnable. And so it works with our types too. Like I said, JS collections, we compile it with Java 5, but it works well with these Java 8 features. So one of our exercises that you see here is we start with customers and we just want to collect their cities. And that one translated very naturally. It used to have an anonymous inner class of function. We just, in fact, the IDE will auto-replace it. And IntelliJ, there's a nice auto-fix, just replaces it with method reference or lambda. So here it just replaced it for us with customer get city, the method reference. Other ones didn't naturally convert into a method reference. So in this second example, we have a list of customers and we want to filter only those that are from London. And so that becomes this lambda here, which is still a lot nicer than an anonymous inner class. But it got us thinking, like, why is this one not a method reference? Could we use a method reference here? And you can kind of force it with this. You could write a method lives in London, and that is the right shape, so you could do it. But of course, no one writes methods like this because it's not abstract anymore. You've encoded the city right in the method. That doesn't make sense in real code. But it's interesting, like you have to conform to this shape. When we saw this, it reminded us of a problem that we had in pre-Java 8 days. Keep in mind, we've been using these functional patterns forever, and we're using our own function and our own predicate. So we would always be instantiating them all over the place, and they're usually stateless objects. So going back to the example of customers and we're collecting their cities, here's what we would do in realistic production code where we had functions that we would reuse. We have this function that goes from a customer to a city, we would turn it into a constant. Because this function It's an anonymous inner class, it's very small, but it's still an object that lives on the heap. You still instantiate it with new, it still gets garbage collected. And so if you're going to reuse it, which is very common, the same pattern gets used by collect and group by and a whole bunch of others. We would just stash it, and our coding conventions would be, if you have a function from customer to string like this, put it on the customer class as a constant, name it by what it's going to, so to city. And we were already doing this for years, and the interesting thing is that this code where you see customer to city looks remarkably like method references. And it was a trick we've been doing just to avoid object allocation. Now the second example with filtering, we ran into the same exact problem when trying to reduce garbage creation. Here we want to filter the customers by some city, and here I've embedded London as a constant, but you have to imagine that London is a variable or a parameter, and this is going to close over it. In terms of the bytecode, the predicate would have a hidden field for that city. In this case, you can't just extract the predicate as a constant, because it has to close over the city, and it's different for each city. It's a different instance. And when we ran into examples like this in loops, we really had a garbage creation problem in some of our most performance-sensitive apps. And so we actually came up with a second pattern to address this. And we call it our with methods because it's named select with, collect with, etc. Instead of taking a predicate, it takes our predicate to type, which takes the object t plus an arbitrary parameter, which in this case is that city, London. And so now the predicate is stateless, but it takes 2 arguments. And so we can store it as a constant. It's called lives in, which is simple because that matches the method that it delegates to. And instead of select, I call select with lives in London. It doesn't create any garbage. And this is a trick that we've been using in Java 5 through Java 7. Now these methods just happen to work perfectly with method references. In the place where I would have used a constant, I can just call lives in. And the bytecode for this stuff can be complicated. It doesn't actually create an anonymous inner class, but you can presume that this sort of pattern will perform better than the Java 7 equivalent. So this increases the number of places we can use method references, and we really love the syntax, so this is kind of exciting. So I would like to see patterns like this on streams as well. Filter and filter with. The name isn't important, we don't have to use that naming convention, but the idea I think is important. All right, I have this framework comparison, and I'm not going to go through every cell here, but the important point about this, the feature matrix here, is that these features stack on top of each other. It's more than the sum of its parts. So I mentioned, for example, one of the cells here is that we have optimized sets and maps. When we built our bi-maps, multi-maps, and bags, we built them on top of our optimized containers. When we did parallel evaluation as well as serial evaluation, it's on our interfaces, it's not through collectors, for example. So we wound up with every choice, it kind of multiplies out, that's why the library is so big. We have eager and lazy evaluation, we have serial and parallel evaluation, and we have all of these iteration patterns that you've seen on every choice and every container type. So it is a big library, but it's very feature-rich, and these things are important in our applications. So think about which of these features you would want to see in the core Java, so that you don't have to use as many collections frameworks as you usually wind up in your class path. All right, to wrap up, here's where you can go for more information. You can, of course, reach out to me directly. I'd love to see more questions on Stack Overflow. We created a tag and we just started answering questions on Stack Overflow, so we watched that tag. It's a great place to interact with us. You can check out all of our code on GitHub. There's the 2 repositories, and our wiki points to all of our talks. The 2 talks I wanted to highlight, though, are the performance one from QCon, where we talk about parallel lazy performance of Java 8 versus Scala versus JS collections, and we have more info on our memory test benchmarks. I just showed 3 today, but we have really detailed benchmarks. You can also check out our engineering site, where we have a few articles about JS collections as well as other engineering problems that we solve. All right, that's all I have. I'd like to open it up for questions.